Well, thanks for coming, and I guess we can start. Now, to rest your minds, yes, the t-shirt says Move Semantics, but in Serbian. It technically half Serbian, Move is still in English, and full translation would be Semantika pomeranja, and not even C++ developers would get it. They would assume it's like some dancing stuff. Funnily enough, if this E had a hat or a half hat, it would be the way it's spelled in Czech. And would you know it? I'm from Serbia, living in Prague right now. But enough about my t-shirt, about me. Now, I like to emphasize this part that to be a teaching assistant, because I see this in a way as part of that, meaning I need you to interact with me. Like, if you are completely quiet, I'm going to assume that either you didn't listen or you didn't understand the word I said. And I go into panic, and not good for anyone. So, like, if anyone can just, like, nod or give me, like, yeah, move it along. But don't worry, I do have at least 3 plants in the audience, and like Victor already did the entire talk about how layout is important for the ABI compatibility. So I say it's gonna be good. With that, I guess we can start. Thank you. So, you have decided to create a class, right? You tried all the other ways, and you just have to. There is nothing else. And yeah, well, you need some member variables, and you need some member functions, some static, some private, public, protected, all the stuff, right? And the way it's usually done is you write struct or class, you write a name, you open and close the braces, put a semicolon, and it's like you open a bag and just throw stuff in there with reckless abandon, just like so just don't think about it. And when you're done, you're like, yeah, it's good. And then sometime someone else comes along and is like, oh, this is a nice bag, I have some more stuff to put in there. Of course, the first thing would be you should probably learn the solid principles, or at least the S of the solid principles, but that's not what this talk is about. This, how many would you agree that this is something like the code you would write? No one. Nice. Nice. Is it because of the exception? Is that what's keeping you back? Okay, so yeah, there is this perfectly named my struct that has 2 integers, 1 double, 3 bools, and a string name, because without it, nothing makes sense. With the name, we at least know what it is. Good. So first, let's start with the standard, and by standard, I of course mean the CPP-ref, because yeah, I'm not gonna read the standard. This is just to set like some terms and basically the rules of the game. Now, first thing I want to emphasize, because in previous versions of this talk I always forget, is that I will not be talking about virtual inheritance because it complicates things, and I only have an hour, and also I try to avoid it if possible. So everything I say, like from this point forward, just assume that there is no virtual inheritance at any point. Now, non-static data members contribute to the size of the object. The only thing that matters to us for this talk are the non-static member variables. And yes, there is also a name data members or member objects, and I will try to stick only to member variables. Hopefully it's gonna be less confusing that way. Other stuff like member functions, and if you define a class within a class, doesn't impact the layout or enum or static data, none of that matters. Like, only thing that matter are the non-static member variables. And this is the simple part, which is that you are guaranteed that the object is going to be in one contiguous chunk of memory. And the first member variable is going to be at the 0 offset looking at the object. You are, however, not guaranteed which member variable is going to be first. But that's the fun part. And you can imagine like the class that I showed previously looking something like this in memory, except that these bools would be smaller, but I was too lazy to adjust the size of the table elements. And last night, we actually had this somewhat lively discussion about languages, spoken languages, not programming languages. And yeah, there was this like a point with Czech and Slovak language where people from Czech Republic can understand Slovak, but or is it the other way around? I don't remember. But the point is, like there is this, there is one way understanding. They are kind of speaking the same language, but not really. And that's basically how I felt reading this part of the CPP-ref and the standard. Like, I know it's English because I understand every word individually, but like the sentences, not so much. So, before C++ 11, you were guaranteed that within an access block, and an access block is all of the variables, like when you write, let's say, public, and then you write some variables, until you write something like protected or private, that's like one block. And you were guaranteed that all of the member variables within that block are going to be laid out in memory in the order in which they were declared. However, you were not guaranteed the order of the blocks, so they could be moved around. Then they changed it, and also like if someone knows if I'm misunderstanding this, please correct me. Like, I don't want to gaslight people here. So, in C++ 11, when reworking pod, they changed this. And now, we are not talking about blocks. We are talking about variables, member variables individually. So, basically, member variables with the same access are going to be relative to each other in the order they were declared, but they could be moved around. And of course, there is kind of an obvious question, which is why? And there is at least I don't know any good answer. Like in theory, yes, the compiler could do some optimization here, and that's probably why they left it. But also think about it, they could change, compiler could change its decision how to lay out data from version to version, breaking ABI constantly, and like we've learned that we don't guarantee ABI, but we also don't want to break it. Luckily, C++ 23 came along, and this is the whole reason why I actually kept this slide. There was this paper which does it actually exactly what it said, makes the order layout mandated, the same as the declaration order, and if you read it, or at least just the conclusion, it basically comes down to this. First of all, no one did this, like no one played around with layout unnecessarily, so either compiler developers are good people or they're lazy, and both are completely understandable. And the second point was that it really wouldn't make sense to like keep this rule, and no one understands like the rationale why we had it, so let's just remove it, and no one is even going to notice. So now everything is as you'd expect. And there is this another paper, and I have no idea what the status is, which basically says, let's add an attribute that is going to allow compiler to, again, mess with the layout. But this time we are actually going to tell the compiler, in which way we wanted to mess with the layout. Like you can say smallest, and then it's going to like solve the knapsack or no backpack problem and figure out the optimal way to order your data. Or I think the compilers are allowed to ignore your attributes, so compiler implementers can stay lazy. Again, no idea what's the status of this. It's accepted, or is it even being discussed? So, next thing, we have this thing that are sub-objects. Member objects, base class sub-objects, and array elements. Don't care about array elements. Member objects are actually member variables, and base class sub-objects are, as you can imagine, sub-objects of base classes. The point of this is that for the purposes of the layout, base class sub-objects and member variables are basically the same thing, and there are going to be examples that are going to illustrate this better. And just for the completeness, of course, if we have sub-objects, we have complete objects, which is things that are not sub-objects. The next thing is that every object needs to have a size, and the funny thing is, it says also, yeah, I copied this like from CPP-Ref. I did not care to write it in my own words. So it says that each object needs to have a size which is non-zero. We are going to, for now, ignore this overlapping, potentially overlapping part, and bit fields we are going to ignore completely. The funny thing about this is it doesn't really say it's unsigned or anything like that. So technically, it can be a negative size. I mean, not really. But if it were possible, it would mean that downloading RAM would be possible. You would just need a bunch of objects with negative size, adding memory to your computer. So it was not a lie. But in reality, yeah, it needs to be non-zero, meaning it needs to be at least 1 or greater. Also, if you don't like the jokes or they are confusing, just let me know, I will stop. And the last thing is, like, there is a lot of text here, so like don't bother reading. It's more like notes for me. If you have two objects of same type and same lifetime, they need to have distinct addresses. Well, if they are different types also, yes, but that's like a more obvious part. This is, again, going to be shown later, but in essence, each object needs to have a size greater than 1, and needs to have a unique address, greater than 0, and unique address. So, yeah, like if you have something at this address, the size is at least 1, so the next object can be at the next address. Of course, link to where you can read this more. Cool, go on. Yeah. The next thing is the alignment. Now every type has this thing called the alignment requirement. It's a size t, and it's a power of 2. And the easiest way to think about the alignment is to think that the address of the address at which the object of this type can be allocated needs to be divisible by this number, which is called alignment. You can use align of, an operator, or a function stood alignment of to get the alignment requirement of a type. And you can also use align as to set the alignment requirement for a type. The limitation of the align as is that it needs to be, well, basically needs to satisfy the requirement of the alignment, which is it needs to be power of 2, and also it can only set higher alignment requirement. So like if you have an int which is 4 byte, you can only set its alignment requirement to 8 or 16 or like more, not less. And we also have a bunch more of these functions. I'm not going to go into them because not really important for the purposes of these talks, but I am going to mention not to use the last one, and like, just don't. And there is also, well, the OS or the processor itself kind of requires, has some like expectations for the alignment. The point of this is that the processor never really loads 1 byte, even though you can address 1 byte is going to read 1 word, which is 4 or 8 bytes. And yeah, we are kind of taught that the objects should fit, if possible, in 1 word, or if it's possible, like, don't get it between 2 words, because then you need 2 loads to read the object, and that's just terrible. Like, performance is just down the toilet, but is it? Is it? So this is from the Lemaire's blog, and I would just like to note this is from 2012. Basically what he did, he took integers of 4 bytes or 8 bytes and just misaligned them to see what are the performance differences. And you will notice that on a Core i7 processor, there is basically no difference. And on Core 2, there is some like minor difference of 10%. Now, 10% is, of course, not that little, especially when talking to C++ developers, but who is using Core 2 processor these days, so don't worry. Other thing is, of course, like you actually need to go out of your way to misalign data, so just like don't do anything stupid and you're fine. With that, we can, I hope, move to examples. Yeah, I got some thumbs up. Yeah, also, like, feel free to ask any questions as soon as they pop up, or if anyone is following the online chat, like, I would rather not get to the end and find out that there is something from the beginning that was misunderstood. So we have inheritance. We have these 3 base classes, and 2 of them have an integer, and then we have the class that inherits from all 3 of them. Of course, all of the examples are on Goldbolt. I assume that presentation is going to be available. If not, it's definitely on Git, so you will be free to play with it. Size of the first is, as we'd expect, 4, because that's the size of the int. The size of the second is 1, because even though the second base doesn't have any data, it still needs at least 1 byte in memory. And the third is, of course, 4. And now the size of the inheritance is 8. Okay, so like no elementary school maths, 4 plus 1 plus 4 is 8. Beautiful. And the reason for that is? Okay, yeah. Maybe someone from the back row, not the first row. Okay, so let's just quickly go through these base classes. The slide says usually, and it says usually because I don't think it's mandated anywhere, but in general, if you have base classes, the sub-objects of the base classes are going to be before the sub-object of the most derived class. And no, sorry, that's actually the next. Yeah, sorry, that's actually the next slide. And yeah, as mentioned, like empty stateless classes take 1 byte, except that they don't really have to, and the compiler can do empty base class optimization. In essence, what happens is that the class, I think the stateless is a better name for the classes that have no member variables. Like, it doesn't hold any state, which means it doesn't really need any space. It needs an address, and we have already addresses for other objects, so why not share? So yeah, the compiler can do empty base class optimization. meaning it can share the space from other parts of the class with this stateless class. And this is where we get to the C++ part, which is it's compiler dependent. Yes, we have 3 major and I don't know how many minor compilers. But I have only played with the 3 major, of course, because, I mean, I can't go through all of them. So now we have a bit different example, which is the second base is the base class of the first and third base. And like I kept the names the same because copy-paste is easier than, renaming everything. And again, second base is size 1, first and third base are size 4. And what is the size of inheritance? So we got 8, 9, and 12. Well, it depends. And of course, that's why I mentioned it's compiler dependent. So if we ask GCC, it's going to say 8. If we ask Clang, it's going to say 8. And if we ask MSVC, it is going to say 12. It's absolutely refusing 9, like in any way. But also, like Victor, you have a bug, so yeah. No, I don't care. Like just for context, Victor, I know Victor from Prague, and he works in Microsoft. He works for works on Visual Studio. But as far as I'm concerned, he works on Microsoft. So like if I buy an Xbox and my controller dies, I'm like going to Victor. I have an approximate idea where he lives, and I know where he works. So yeah. Good. But we were told that anything we can do, well, not anything we can do with the inheritance, we can do with composition, but we should favor composition over inheritance. So first, second, and third base are the same, and now they are not base classes, they are member variables. And the size is? We got 12 and 16. And 12 is correct, and it's correct because alignment. Yes. So I haven't mentioned it like first time I went through alignment, but the alignment of this entire composition is going to be the same as the alignment of its largest member variable, and like it goes down through the inheritance. So in this case, it is going to be 4 because both first and third are size 4 and have alignment requirement on 4. So yes, we are going to have basically 9 bytes of useful stuff, and then we are going to have 3 bytes of padding. So they lied to us. We cannot do empty base class optimization with inheritance. Or can we? Can we? I don't know. Yeah, that's also a good answer. I don't know. That's why we're here, isn't it? So, since C++20 we have this attribute, no unique address, and I like it because it actually perfectly illustrates what the purpose is. Like no unique address. I have this second base, but it doesn't really. It's a member variable, but it doesn't really need any space, so it doesn't need a unique address. So yeah, it can share with one of the others, and yeah, everything stays the same. And composition is now 8. We have effectively done the empty base class optimization. A bit more about this no unique address. Yeah, so you apply it to a member variable when you declare it, and this is like, if you remember, I mentioned that the size needs to be greater than 0 unless it's potentially overlapping. Well, this makes it potentially overlapping, and now it basically shares space, or well, shares address with some other member variable or like base class. And yeah, there is also this part that if the member is not empty, then the padding can be reused, but haven't played with it, and I don't think anyone really has. And also, it's since C++ 20, and also Microsoft, because they had it from I don't know when, they still use the MSVC : no unique address, while the GCC and Clang just have no unique address. So you can use a macro for this. We love macros, don't we? And now we get to like more interesting examples. Now this doesn't really make sense. Why would I have 4 stateless like objects? Because they don't carry any state. Like 1 should be enough. But let's just have fun, right? If you do it this way, they are in the middle, like all 3 compilers agree. It's great. If you put them in the beginning, then again, all of them agree. Also great. If we put them in the end, they disagree. And Microsoft actually here does the better thing, I guess. But what if we have 5? Because 4 is just not enough. Now, in this case, again, GCC and Clang are in sync, so they basically do the same thing. And Microsoft just doesn't want to play along. Same thing happens if you put them in the beginning, but if you put them in the end, then Microsoft does the right thing. You know, one day, we hope all that compiler implementers are going to agree on how they do this stuff, so we don't have to go to Godbolt with 3 compilers and like see what happens. But not today. Not today. So like donate to Godbolt, please. And with all this craziness of all these rules, we have this thing that's called the standard layout type. Now the purpose of it is that if you follow the rules that this thing requires, you are going to get the same layout from all the standard compliant compilers. Now the rules are no virtual functions and no virtual inheritance. If you have base classes, they all need to be of the standard layout type, and you cannot have the same base class twice because, well, as if we've seen, empty base class optimization may not work. And if you have member variables, all of them need to have the same access, and all of them need to be in the same base class or in the most derived class. And there is this is standard layout type trait that you can use to check if your type is standard layout. And there is an example for like anyone who wants to go and play with it. But if you want to take a closer look at like how it's actually laid out in memory, first thing you can use is this offset off. It's actually from C, it's a macro. So you put the type and you put the name of the member variable, and then it expands and gives you the offset of that member variable within the type. And example from the CPP-ref, we have this struct S. It has a char, a double, a short, and another char, and you call offset off, and it gives you the offset. So like the char is at offset 0, which basically means it's at the beginning of the object. Then the double is at 8 because of the alignment requirements. Short is at 16, again, alignment requirements, and then the next char is at 18. Pretty obvious, I would say. Yes. Yes. But that's not enough. That's not fun enough, because we have no information about the base classes, and we want to know. We have to know. We lose sleep over this. So all 3 of the compilers have these flags, and like just a kind of a fair warning, these are compiler developer debug flags. So not something you should use or can practically use in like build. but they are going to dump the layout of the classes in the, well, either in a file for the GCC example or in the terminal for the others. Yeah, like one note for the Clang and GCC for the Clang. So it's dump record layouts, but depending on the version, you're either going to need to use this CC1 or Xclang. I don't know when they changed it. Like when I originally did this presentation, it was CC1, and then in the meantime, it changed to, it stopped working, so I moved to this Xclang. And for the same thing for the GCC thing, it's like either fdump lang class or dump class hierarchy. And also the GCC thing is going to dump to a file that's going to be named like the name of the file that's being compiled .class. So you can't use it in Compiler Explorer. And MSVC has stayed consistent with the name. And this is, here I've used the examples from the Clang because I find their output the prettiest. And also, like GCC one was pretty sparse with the information. Now I'm just going to use the, or I'm not. Can we? Yeah, okay, sorry, I guess not. So yeah, I mean, I actually wanted, I just wanted to use the cursor because of the online people, but the projector is not going to work. And yes, I do care about people that are here more than online people, so. On the left-hand side, we see the offsets, and then in the bottom, you see the size of the D size. I forgot what that is, but it doesn't really matter. What matters to us right now is the size of and the align, and the NV size is like non-virtual size, and NV align is non-virtual align. For us, it's all the same, simply because there is nothing virtual going on here. And then you see the name of the struct, and then you see its member variables, and on the left-hand side, you see the zeros or 4, 8, which are the offsets. Yeah, so here are the first, second, and third base, and then there is this composition with no unique address, which is just like the first example of a composition where we did not use the virtual inheritance, no unique address. So we see that the first base is in the beginning, and the int b from the first base is like at the offset 0, like right at the beginning. And then at offset 4, we have the second base, and it also like says it's empty. But then at 8, it says it puts this third base, and it's of course the C, its member variable, and so like all in all we get the size of 12, and we get the align requirements of 4. If we use the no unique address, then we see that the second base, or the member variable of type second base, is at the same offset as the first base, or the int b from the first base. So it's exactly as it says, no unique address, like it's using the address of this thing because it doesn't hold any state, doesn't need any actual memory, and after that, the third base. And then this is the inheritance, and like, as I've mentioned, the base class subobjects and the member variable subobjects for the purposes of the layout are the same thing, and it's, I think, best illustrated in this example with no unique address, because you will notice that the only difference is in this case, when we use inheritance, it says base in the brackets, and here it doesn't. But other than that, everything is exactly the same. And this is the class from the beginning, the MyStruct, the infamous MyStruct. We see, okay, int bool, double bool, great. But this is, I think, the most fun part of this dumping the records layout, is that we now see the string, how it looks, and how it's basically implemented, at least this part when it comes to the layout. We see that the string has this alloc hider and data plus, and that thing, that alloc hider, has this base class, which is an empty base class allocator, which is again which again has this empty base new allocator for the char, and it has a pointer MP. And then there is string length of the science type, and then, yeah, there is this, we also see this like small string optimization, the union of the car buffer and the size type allocated capacity. And also like the entire size is 64 and the alignment requirement is 8. And also like you will notice that this, like, okay, the first two bools are, well, okay, bool is just true or false. So it technically needs 1 bit, but we kind of need the entire byte. We cannot have size of 0.1. We said it needs to be like greater than 0, but really needs to be a whole number. But here, because of the alignment, it's 4 bytes. So instead of wasting 7 bits, we are wasting 31 bit. And the worst case is actually after this double, because then this third is value 3 set is at 24, and the string starts at 32, meaning that we are wasting 7 bytes and 7 bits. Really wasteful. And now let's take a look at the examples that kind of confused the MSVC. The inheritance, which has size 12. Yeah, like, I have no idea what happened here. So you see that the first base and second base, it's fine, it's at 0, and then for some reason the third base is at 8. So don't know why it put like the padding there. We see that the Clang did the same thing for the start, but then put the third base where it should be. So I don't know, fix it, Victor. No, that would be ABI break. Don't do it. Or actually, you can use this as a pin that's going to open the floodgates and like, oh, we break this, like let's break everything, destroy the ABI. And this is the example where they kind of agreed on like the size. Well, they at least agreed on the size of the object. But we see that Microsoft is at least consistent, meaning that the S1, S2, and S3 are going to share the memory with the F. Like it's going to look before it's going to look to the object that's declared before to share the memory with it, while the Clang for the S1 shares with the first base, but the rest share with the third base. Like, seems pretty arbitrary, but you know, it's how they did it. So yeah, it kind of seemed like they agreed, but no, we don't do that here. And finally, yeah, sorry, forgot about this slide, but for now, just don't assume assert, like you don't know what the compiler is doing, you know. Do something like check the offset off or check the size or is standard layout or whatever, just you don't know what they're doing. Any questions? Just needed an excuse to drink some water. Finally, the performance, the only thing we really care about, right? right? Right. Now, I have these two very simple classes. One is good data and the other is sinful data. Now, the sinful data is sinful simply because it's wasting space. In the good data, we have integer and 2 bools, and because of the alignment requirements, we're going to have 2 padding bytes. But in the sinful data, we have also 1 integer and 2 bools, but because there is 1 bool, then 1 integer, then another bool, there is going to be bool, padding, integer, bool, padding, meaning sinful data is going to be 12 bytes and good data is going to be 8 bytes, 50% difference in size. Terrible. Now, the only things that I've implemented for this very simple structs are the constructor and less than operator for the sole purpose of illustrating that they are functionally, if that is the correct word, the same, meaning they encode the same amount of data and the constructors are the same, they take the same arguments in the same order, simply because the code would be simpler, I don't need to implement things twice. And the less than operator is implemented because, of course, there is going to be a sort, and I don't want to use the spaceship operator because I want the values to be compared in the same order, leading to the same evaluation. So I don't want the performance of sort to depend on the number of swaps. It should be like the same. It should just depend on the fact that they are not laid out in memory the same. Cool? Yeah. So for the setup, Ryzen 7000, whatever. Yeah, like I originally did this like a year ago when like this was a Flex. It was completely new processor. Now it's just sold. Not that fun. There are new ones. And Manjaro, I don't remember what version was when I did the test. When I did the benchmark, but it's just to show that I use Arch, which is required. It's like the most basic version. Like it's like Ubuntu. I just installed it. Like everything is default, but it's Arch, so I can say I use Arch. That's the important part. I use like Google Benchmark because it's basically the industry standard, and for each data point, there are 100 iterations, and the data sizes go from 100 to 1 million with 100 increments. Generate data is going to create a vector, and then it's going to run a reserve space, and then it's going to random generate values for the good and sinful data. For each is just going to iterate through all of them. Maybe there is some like basic operation happening. Sort is just std sort, and accumulate is just std accumulate. And it's on Git, so you can go and like complain about my code style and tell me what's wrong. I will ignore it, but you know, if it makes you feel better, do it. Now I do apologize for the graphs. They are not the most visible, but like I just dumped all of the benchmark info into a CSV file, and there was this Python script I found online that generated the graphs, and I couldn't be bothered to like fix the size of the fonts and stuff. So yeah, it's Python. I don't, unless I have to, I don't do it. But in essence, what you need to know is that this x-axis is logarithmic, so it goes from like 100 to 1,000 to 10,000 to 100,000 to a million. And this is just CPU time. This doesn't really show much. This is the benchmark for the generate. This is the relative speed, and well, the blue line is the good data, which is supposed to be the baseline, which is supposed to be the better. But we see here that the sinful data is, for the most part, actually better. The time when it gets like close to the good data is basically when we get out of the cache, and when we get out of I think it's when we get out of L2 cache, and then when we get out of like cache entirely, it's just chaos. That's what you usually see at the end of the graph. But we see here that the sinful data is actually better in this case. So, you know, it's like they always say, measure before you optimize. And now we have for each. And in this case, we notice these bumps. And these bumps most probably coincide with when we get out of L1 and L2 and then L3 cache. And we notice that like consistently, the sinful data is going to get out of the cache sooner than the good data. Then like by the time the good data gets out, the performance pretty much evens out until we get out of cache entirely, and then it's just chaos again. And in this relative comparison, it's, yeah, you see these bumps. The bumps are basically the places where the sinful data has left the cache, but the good data hasn't yet, and then they catch up, and then in the end is just the end. And we have sort. Yeah, this doesn't really show much, but relatively speaking, it's usually faster to sort the good data compared to the bad data, but the difference is somewhere like 2-3%, which I guess should not be surprising because we randomly access stuff, so we don't benefit from cache locality or stuff like that. Except for this very specific case, I don't know which value is this, but again, it's 100 iterations. It wasn't just one-off. For 100 times, it was 35% faster to sort the sinful data than the good data. Don't know what happened there. And we get to the accumulate, which is the only one that did what I wanted it to do, to illustrate how good it is to have like a good layout. Here it's like it's consistent, right? It's just consistently better to have this good layout compared to the bad. And in relative, we see that it's not just better, it's much better. Again, I don't know if you can see the numbers on the left side, but it basically goes up to like 4 times faster with the, 4 times faster with the good data compared to the sinful. Any comments, surprises, wishes? Nothing. Perfect. I love the cough, it was like perfectly timed. Like. And yeah, usually I just like to leave references for the stuff I've used if you want to go into more details. The first talk is actually going to go into the layout when you have virtual inheritance. If you're interested in that, go check it out. The rest of the stuff are the blogs I've used and, of course, CPPRF. Which, you know, may not be the best place for learning C++, but if you are interested in like concrete information, it's good. And yeah, I'm not like gonna go on Twitter or Facebook and argue with people, so you will not find me there. But if you wanna shoot some zombies on Steam, I am there. And yeah, with that, I'm done with my part, so I'm open to questions.
Hi, thanks for the presentation. It was very nice. I just have a question though. When you present the good data and the sinful data, if you pack the sinful data, would you expect to get the same results, or will it behave as the good data?
Yeah, so I would say yes, but let's just go back. I didn't use back because like you shouldn't, I've said it and I will repeat it. Yeah, like my assumption here is that the size is the only factor that contributes to the performance. So yeah, like maybe there is something in sense that the int is before the two bools, meaning like in the order in which they are accessed. Like for the less than operator, we access the int and then we access the one bool and the second bool. So maybe because the bool is before int, they are, you know. But I think like with the modern caches, it should be big enough to fit it. It's 8 bytes. It's like one word. So I think that like if they were packed, it would be the same performance.
Yeah. Okay. Thank you.
Yep.
Hello. Hello. Good presentation. Would you say, in terms of your results, could you say it's inconclusive? There's no real conclusion we can draw from this, I suppose.
Yeah. If you mean the performance.
Yeah.
Yeah, it's inconclusive because I did the same test on my other computer, which is some older Intel processor, and some other operating system. It's like Ubuntu something, and the results were different. Very much different. And also, like in my original talk on a local meetup, I did the benchmark live, but instead of having so many iterations, because it took like 2 days to run all of them, I just did like 100, 1000 and stuff like that. And in that case, it was very consistent in terms of like, yeah, the good data was always better. In this case, when you do 100, 200, like if you have more data points, more runs, then it gets the story is a bit different. So yeah, it's not the perfect benchmark by any means. So like, if anyone wants to like criticize, Git is there, and yeah, it's somewhat inconclusive, but. It's also to illustrate the thing that has been said many times: measure before you optimize. Like maybe you have, maybe you have exactly this number of elements where you have insanely better performance with sinful data, and you just do that.
Okay.
Have you done an analysis of data consistency? So you mentioned that especially once you're leaving L3 cache, that it's all over the place. Did you see a big jump in speed consistency, or how's the overall consistency here?
I honestly haven't done any like extensive analysis.
Okay.
This was supposed to be like a very short, fun benchmark.
I kind of assume that the compiler is no longer allowed to pack the bool values because it introduces a data race. If you access the bools from different threads, so you would have to synchronize because you only have right-size access.
This is possible. I don't really know what the compiler
Okay,
is.
so why aren't we making fun of it like vector of bool? Because it prefers the dense layout over efficiency.
Yeah, I mean, I'm not going to comment on vector of bools, so I honestly don't know. Like, also, padding is not that bad because, like, this is the biggest crowd I've talked in front of, but there are so many empty chairs that it's like it's half empty room, so it's not a big deal.
Okay.
So, yeah.
Can you go back to the slide where you show the comparison operation?
Which one?
For the sinful data and the other one.
You mean the code?
Yeah, the code. Did you use that same comparison for the sort benchmark? Or is it on this? Is a different one on the slides?
Yeah, it's this. It's
okay,
this
because
less than.
I think that might explain things because I don't think it's consistent because you can have one value that is smaller than another, and if you do the comparison in the other order, it's still 2. Because if value of the first one is smaller than the value of the other one, then that will return true without checking the bools. If you compare it in the other order, then that will return false, but you then compare the booleans, which can still return true. So you get an inconsistent result for smaller, and that violates the assumptions of sort.
Okay.
If I'm not very mistaken, and if I have explained it properly, I'm not entirely sure.
Right, so like the whole reason I implemented the less than operator is because, and also the reason why I implemented the constructor is that I use rand, like the C rand, with the same seed every time. So the idea is that the data is always going to be generated the same. So basically the values of value B1 and B2 are going to be the same. And then if I call the less than operator, it should evaluate the same. The basic idea is that, like, if I have the same data with the same way of comparing, but with different layouts, what is the difference in the performance? So I don't think there is any inconsistency here, but if anyone disagrees, speak now.
Yeah, maybe mistaken. Maybe I misunderstood something. Sorry, thanks.
Okay.
Need to get ready. Hi. I'm not sure I get it right, so maybe you can kind of reiterate the point. So does using a 64...
Sorry, I said ask questions as they come up. Don't
okay.
No, like...
I'm sorry.
This is precisely the reason I said just like ask as soon as you...
But I believe in you. We can do this. So yeah, does using a 64 environment versus a 32-bit environment make it worse or better? Because I understand if a Boolean pushes a integer because they don't both fit in the same 4-byte alignment, but if you have 8-byte alignment, does that mean you can put two integers densely?
So okay, for the OS part, like the 4-byte word is just like how much the processor is going to load. So okay, I think I get the point. I'm not sure. Yeah, I guess like if it's 8-byte, then everything is going to fit into one word. It's going to be better, but. It's like nowadays it's more about the cache line. It's like more about the cache line and cache size than it is about the word size.
Okay, thank you.
Okay, I'm gonna to the end. Well, yeah, I guess that's it. Thank you.